Smithy and Lukey, right?
Odd names.
Let's see if I can find me. I can find it. Oh, no. All righty. Let's see.
I know, because I use the spelling. Why do you have why do you want to know about my kid? I said, oh, not on the TNT.
Good morning, everybody. Hopefully we're doing fine this morning. One thing I've noticed lately is that it's really dark in the mornings. And I'm not used to it at all. It's crazy for me. So, okay, I'll get on with stuff here. The subject of the day is equilibrium, right? Chemical equilibrium. And basically, that means going through a solubility product, some, basically review, but getting a little bit more into solubility and what that means. Also in the context of separations. And then we'll talk about complex formation, because complexes foil, they defeat the approach of separation by precipitation. So You guys are all familiar with the equilibrium constant, right? For any reaction, A plus B goes to C plus D, right? There is, any, and for any reaction, you could write like this. It's a balanced reaction, it's valid. There's an equilibrium constant, rather, K, that is equal to this value, right? And what intrigued chemists, and what still intrigues chemists, is that equilibrium constant is, in fact, constant, right? That, whatever happens to any individual quantity, like you could be removing D, removing the product D, then more reaction will shift. This reaction will shift until these concentration products equal K again, So I don't know, it's a sort of a short point, but it's important, right? Because the equilibrium constant is constant. Now, and you'll see in a moment why, because it's tied to the free energy, to the thermodynamics of the reaction. And so if K, one thing that we say is that the reaction is favored if K is greater than 1, right? That means it favors product over reactants. And, it's disfavored if K is less than 1, right? K is a positive constant. There's no such thing as a negative K value, right? Because first of all, you're raising these values to powers, etc. So, so it's positive 0 to infinity. The constant itself is dimensionless because C here, this close bracket C here, this really means C over its standard concentration, right? So like it's typically 1 molar, one capital M here. If it's a gas, it's a pressure in bar, and then if it's something in its standard state, like it could be liquid mercury or liquid bromine or, solid sodium chloride or it could be pure water, right? Then what we do is we jigger the system and we say, well, that means that we're just going to define that as standard state, as unit concentration, right? And so what happens is that gets baked into the K value, but it doesn't violate any other principle that we're using. Okay, so that's pretty much it. Concentrations are molar, moles per liter. Pressures are bars. Everything else is unity, pure solids, pure liquids, and solvents are unity. Now, if you talk about the reverse reaction, you just flip the K value over, right? And then if two reactions are added, like A goes to B and B goes to C, so A goes to C, then the new reaction, A goes to C, is the product of Ka and Kb, right? So maybe I should sort of write that out there, but I think that's fairly clear, and we're going to do examples of it. And if N reactions are added, then the overall equilibrium constant is the product of the N reactions. So that's a restatement of number 2. So if A goes to B, B goes to C, C goes to D, then for the overall reaction, A goes to D, the equilibrium constant is equal to the product of equilibrium constant 1, 2, and 3. So we'll see some examples of that shortly, right? So, for example, we have the autoprotolysis of water. This is the autoprotolysis of water. H2O makes H plus plus OH minus. And the Kw for that is always equal to H plus times OH minus, right? So this is something true about water, that for a given temperature and pressure, actually, you could, and what we're going to talk about is true at 25 C and atmospheric pressure, right? Then it doesn't vary dramatically, but it varies a little. But for water, the product of the H plus and the OH minus concentration is always equal to Kw, right? So if you make a solution acidic by raising the H plus ion concentration, the OH minus concentration drops, such that the product of these two is always equal to about 1.0 times 10 to the minus 14. So we can, for example, think about the following type of problem here. Oops, oh no, it's so messed up. So given that, so we could say, given that for the reaction, ammonia, aqueous ammonia plus water makes ammonium ion plus hydroxide ion, right? What that is, it's the combination of this and this. So we want to find the K for the reaction. NH4 plus makes NH3 plus acid, right? So that is an example of how to combine equilibrium balances, right? So first of all, we want to say, well, H2O makes H plus plus OH minus, right? Ignore the slashes for now. This is Kw, right? And we also know NH4 plus plus OH minus makes NH3 plus water, right? And this K value is the reciprocal of the KNH3 that we defined earlier, right? So what we can do then is we can say, well, we have the K for this reaction and this reaction. And now we can add them up, right? And when we add them, the water is a reactant and a product. So we can cancel it. The hydroxide is a reactant and a product. So we can cancel it. I mean, we can write them in here, but it would just be silly. Water plus that makes that plus water, you know? And it won't have any impact mathematically either, right? So that's the meaning of canceling it, right? It's because it shows up as reactant and product. And there's the OH minus showing up as reactant and product, right? So we can cancel that. And the net reaction that we have is NH4 plus makes H plus plus NH3, right? And this is a valid balanced reaction. It's the aggregate of these two reactions, or the sum of these two reactions, I should say. And the equilibrium constant for this new reaction, K, is equal to Kw times 1 over K NH3. And you can just plug in the values, 10 to the minus 14th plus, I forget what that one is, 10 to the minus 5, and you get 10 to the minus 10, right? So, so that is how one goes about combining these equations, right? So now we see here ammonium rather, acting as an acid. And ammonium as an acid has this very small exponent here, right? Whereas ammonia, acting as a base, has a relatively large, oops, I killed PowerPoint. Oops, cancel, has a relatively large, 10 to the minus 5, like 5 orders of magnitude greater equilibrium. So that's so that basically bespeaks the fact that ammonia is a reasonable base, but ammonium is a terrible acid, right? That's a concept we're going to come back to a bunch of times. It's like ammonia is a good base. Ammonium is a terrible acid. So if we take a look at this reaction here, ammonium makes H plus NH3. Which of these are favored, reactants or products? Let's see. Usually we have a couple of vocal dudes here, a couple of vocal students who always chime in. Hence, I know they're missing.
You got to check out the chat. Everyone's answering in the chat.
I'm looking at the chat. Oh my gosh, it just showed up. Omar, reactants or products? Okay, reactants. Right, reactants. Good. Excellent. Good. So this guy here is favored. Thank you, by the way. This guy here is favored, and because the equilibrium constant is product over reactants. Excellent. Yay. Okay. So let's do a test ourselves here. For the reaction, lithium plus water makes lithium hydroxide aqueous plus H plus. So I just want to say here that this is a completely new type of reaction here. This is a metal ion acting as an acid. I don't know if you guys have ever seen that before, but this is a legitimate type of reaction that's really common. Metal ions they're described as Lewis acids because they seek out lone pairs. And when they complex, like lithium, when it complexes with water, it will oftentimes just let go of a proton. So like it's like the O in H2O is happier making a bond of lithium than with H plus. Okay, so it's actually not true in this case because the K value for this is 2.3 times 10 to the minus 14. It's almost the same as KW. Right? So, and I don't really know exactly what that means, to be honest. But it means that the reactants are strongly favored, right? Because products over reactants means reactants are strongly favored, right? So let's do this exercise here to find the K value for lithium hydroxide makes lithium hydroxide aqueous. So lithium hydroxide aqueous, right? This is another weird twist in this problem because lithium hydroxide aqueous, it's not the same as solid lithium hydroxide. This is a molecule that is soluble in water, you know? So don't confuse this guy with lithium hydroxide solid, you know, and it's not really common, you know. I'll always try to point it out and everything, but aqueous lithium hydroxide it's not in any kind of standard state here. Okay. Here are the things here. Let's see. So we've got lithium plus water makes lithium hydroxide plus H plus. And this K value, call it a K1, is equal to 2.3 times 10 to the minus 14, right? Oops, sorry, let me adjust something here so that all this blah, blah, blah makes some sense, right? And then we've got, so now we've got, we know water, right? H2O makes H plus OH minus, right? This is KW, and that's equal to 1.0 times 10 to the minus 14, right? What we want to find is Li plus OH minus makes Li OH aqueous. This is K2 and it's equal to something, right? So the trick here is to see how to combine this guy, combine say 1 here and 2 to such that it adds up to this guy here. And basically what we're going to have is we need to cancel the water. We need to cancel the H plus. Right? So we want to write this one backwards, right? So we can have, we'll call this minus 2, right? This will be H plus OH minus makes H2O. Right? This is K minus, oops. This is K minus W, which is equal to 1 over KW, which is equal to 1.0 times 10 to the plus 14. Okay? K minus W here. So now if we take, and we add reaction 1 plus reaction minus 2, right? And what we're going to have is Li plus H2O makes LiOH plus H plus, right? These are all aqueous. And then H plus OH minus makes H2O, right? I'm going to add these guys up. You see H plus is a reactant and a product, so they cancel. So and then the water cancels here, right? Water cancels out. So now what we're left with is Li plus OH minus makes LiOH aqueous. That's the one we're looking for, right? So the K value for this is, we can call this K2, right? That's what we defined it up here. This will equal K1 times K minus 2. Right? So this will equal K1 is 2.3 times 10 to the minus 14. And K minus 2 is this guy here, and this is 1.0 times 10 to the plus 14. This is just 1 over KW. Right. And so this reaction here has the equilibrium constant of 2.3 times 10 to the 0. Right? 10 to the 0 is 1, right? So this is 2.3. QED, right? So let's see if I got that right. Okay, well, I hope I got it right because there's no answer here. Okay. So, all right. So let's talk about the relationship between equilibrium and thermodynamics here. So, So thermodynamics, it's like bookkeeping for chemistry, right? And you recall how there's a whole bunch of different properties we can assign to different reactants and products that we can always just add them up and find a given uh, a given reaction's properties. So one of these guys is called enthalpy. And enthalpy, you may recall, is heat absorbed or released when a reaction takes place under constant pressure, right? You think, where did they get this crap, you know? Constant pressure, why? Well, constant pressure is one of the sort of extremes of like an engine. If you have a reaction that takes place in a piston and it releases heat, right? It makes steam or something, right? Then under constant pressure, it'll expand, right? You can do a little bit of work on your surroundings. So that's where the idea of constant pressure came from, right? Useful to chemists, because normally we're not making steam, we're not doing this crap. But it turns out that delta H is a state. So you can just add it up, and any reaction you do open to the air, the H value of the reactants and products you can get from tables, you can calculate delta H beforehand, right? All right, so enough blah, blah, blah. That's not really relevant to this class, but hopefully it adds a little context. So if delta H is positive and heat is absorbed, and the reaction is endothermic. So there are many examples, they're not the majority, but there are many examples of reactions which are spontaneous, means they go forward, but they're endothermic, so that when they go, they cool down, right? Any athlete knows that they have these chemical cold packs, and you can break them open and they get cold. That's an example of a reaction that's driven by the entropy. We'll get into that in just a second. And so that's a positive enthalpy. And then if delta H is negative, then heat is released and the reaction is exothermic. That's one we're more familiar with, right? Burning of methane, in a rocket engine or something, So delta H naught here, this is the heat absorbed or released when the reactants of end products are in their standard states. That is typically around 1 molar. It's actually exactly 1 molar, not typically, it's exactly 1 molar, right? Or solid, or neat liquid, the undiluted liquid, or things like that. So, all right. So now entropy. Entropy is well, first of all, let me talk about it in a way that I understand it, which is imperfect, but it's a way to understand it. So entropy changes occur when things can happen, and they happen, right? It's like if you have like a checkerboard with some checkers on it, maybe 10 checkers, and you just kind of and it's like shaking around a little bit. Maybe you're in a car or something, and the checkers are going to move around, right? The checkers will move around on the board. Oh, okay, Alvin. Thank you for mentioning. Alvin's going to be a fly on the wall. So that's good. He's psychic, because I was going to ask someone to respond to my amazing analogy of the checkerboard in the car. Thank you. So Delvin said something, but we couldn't hear it. So that's because, and it happens because it can happen. There's a little bit of energy around, and that the energy of the bouncing car is like temperature, and then delta S. When the checkers move around, their entropy increases, right? So that I mean that I don't know exactly if that's true, but this is the general idea that things happen because they can happen, right? Certainly, if they're in a I don't know, actually, let me not go there. So so one thing we can say is that a gas has a higher entropy than a liquid, right? So if you have a closed system with some liquid, and that liquid evaporates, then the molecules in the liquid increase their entropy by evaporating. It's fairly straightforward. I mean, it can happen, so it happens, you know. And a liquid has a higher entropy than a solid. You know, so if something melts, for example, like then it will be increasing its own entropy, right? Phase changes here. Okay, so and delta S naught is simply that value of S, of delta S, that happens when all species are in their standard state. Delta S is positive, products have greater entropy. Delta S is negative, positive products have lower entropy. So it's a funny sign convention, and we'll put it all together here. So remember now that enthalpy is not always easy to measure, and entropy is not easy to measure. And what's even harder to measure is actually free energy. But folks have worked through this, and it makes sense that the Gibbs free energy here is it's actually defined at constant temperature, right? And it's also constant pressure because delta H is constant pressure, right? So constant temperature, constant pressure, you can come up with a third state variable called G. And G is delta H minus T delta S. Whoop-de-doo, right? So who cares about this? But the thing about the Gibbs energy is that it tells you the direction that a reaction will go towards equilibrium, right? So, so the sign of delta G tells you whether the reaction will go in reverse or if it will go forward. By the way, how's my audio? Is it okay? Okay, I'll assume it's okay in this. Sometimes, thank you, Michaela. Sometimes it gets weird and I have to like cycle the power off of it. But anyway, so delta G is what sets K, right? So K is equal to e to the minus delta G over RT. And this is actually why when you add delta G's, you multiply K's. You know, this is where that all comes from. And the exponents is all just coming right from here. And I'll do a little blurb for you on that next time. I just a little bit unprepared right now. But so if delta G is positive, then K is less than 1. If delta G is negative, then K is greater than 1. So negative delta G favors products, right? So so here K is e to the minus delta G. So if delta G, and it's delta G naught, right? So K is related to delta G naught for a reaction. So if delta G naught is negative, then minus delta G naught is positive, and e to a positive value is greater than 1. E to the 0 is equal to 1, and e to a negative value is less than 1. But k is always positive. It's lovely how these things work out. Right? So that's how, so k and delta G are related by this relationship here. So, all right. And so this kind of goes into Le Chatelier's principle here, which is review for y'all, of course, but I'll go ahead and talk about it briefly. Bromate plus chromium 3 makes bromide plus dichromate, right? And so if we want to write the equilibrium constant for this reaction, a couple things come to mind, right? First of all, water, even though it takes 4 of them, we're considering water to be in its standard state, right? So, and it's a good approximation normally, right? Because normally water is about 55 molar. So if these guys are like, let's, even at an extreme, they can all be, say, 1 molar. The water's still going to be maybe 54.5 or something like that. Who knows? Anyway, it'll be close to 55, right? So we're going to omit the water term from the equilibrium constant. We're just going to take the products, bromide, dichromate, and H plus. We're going to raise H plus to the 8th power, right? And we'll take the bromate, or the, I'm sorry, this is, come on. It wants to edit the stupid thing again. It's going to take the, yeah, this is bromate. Bromate and chromium 3 will be in the denominator, and this guy has an equilibrium constant of 10 to the 11, meaning these guys are strongly favored. Kind of surprises me, actually, because bromate must be a really strong oxidizing agent, right? So if we have a reaction like this at equilibrium, right? Whatever it is, these reactants, whatever their values, have come to equilibrium, and therefore their product here is equal to K. And we add chromium to that reaction, then what will happen is that more bromate will be formed, right? Because, I'm sorry, this goes up, so it will consume more of this and make more of that, right? And so this stress that you place in the system, the system will deviate from equilibrium, and it will reassume equilibrium by reacting further, by making more products, right? So the system will shift to form more products until Q equals K. So Q here is just this thing. Whatever these values happen to be, it's called the reaction quotient. Q is this, right? IMQ, right? If I can make this guy good. So Q here, this is Q. And when Q is less than K, then the reactants and this reaction will proceed until they're equal to K, right? That's how equilibrium will be reestablished. That's how this works. Ain't that amazing? Oh my God. It all works. It's amazing. So here's sort of a restatement of all that stuff, right? And it also works with enthalpy, right? Because enthalpy has this heat term, right? So if delta H is positive, then what you're saying is that heat plus reactants make products. And so heat will, if you add heat, it will favor products. And if delta H is negative, if you add heat, it will favor reactants, right? It's another equilibrium concept that works with Le Chatelier's principle. All at constant pressure and temperature, because that's the way we like it, right, as chemists. Okay, so equilibrium, just for the record, describes it describes the lowest energy state of the system, right? But it doesn't say if it will actually happen. You know, it generally won't go the other way, but it can be that things are stuck. A chemical system can be stuck kinetically. And so it'll go a certain way and then it'll get stuck. And then it will just be out of equilibrium. Q and K will not be, well, the reaction quotient Q will not equal K. And so those are non-equilibrium reactions. And we're not going to talk about them, but they're everywhere, trust me. Like the atmosphere, thank God, is a non-equilibrium state. You know, we've got O2 and N2 coexisting without making N2O4 and all that other stuff. So thank God that happens, right? And million years is like, no, how about a trillion years? You know? It may never happen, right? All right. So so a large equilibrium constant does not imply that a reaction is fast. Right, so anyway, just highlighting, just might as well highlight the whole line there. Okay. So let's talk about a solubility product here, get into some of the meat of what we're doing here. And for KSP here, solids are omitted from the expression. So if you've got, for example here, calomel, mercurous chloride, makes Hg2, 2+, makes this weird dimeric mercury ion, plus 2 chlorides. And the KSP for that guy here is equal to the product of Hg2, 2+. Remember, this is a single chemical entity, right? And times the chloride ion quantity squared, right? So, so in a saturated solution, there'll be excess undissolved solid. And if you have an excess undissolved solid of Hg2Cl2 and water above it, then it will dissolve until this concentration product equals KSP, right? And so, so this is how KSP works, basically. And so let's take an example here. If we have this salt, if we have calomel here, and it is actually in a solution of water that already contains 0.1 molar KCl, right? Oh my gosh, here, so right? Now, things are a little bit different, but they're actually simpler, right? Because we can assume for the moment that we know the chloride ion concentration. So we got KSP equals Hg2, 2+, plus Cl minus squared, right? And that's gonna, so we can solve for Hg2, 2+, right? And that will equal KSP over 0.1 squared is 1.2 times 10 to the minus 16 molar, right? So let's just think about this for a second here. We've got a beaker with water. We've got some calomel in there. Got some calomel in there, and it's dissolving. And in this water, whoops, there we go. We've got water, and it's dissolving. So let me actually start over, make this a little bit bigger. We've got some water. We've got solid calomel here. And this stuff is dissolving. When it dissolves, it makes Hg2, 2 plus, and Cl minus, right? And in this solution, we already have K plus and Cl minus. We have, I forget what exactly the source of Cl minus, but K plus is the spectator, right? And we know that Ksp, or Hg2Cl2, what's the value there? That's 1.2 times 10 to the minus 16. Right? So now we know that when Hg2Cl2 dissolves, it will augment this chloride ion concentration a little bit, right? But let's just look at this here, and we know that it's going to be a very, very small value, right? This solid makes 2 Cl minus, right? And we know that because the product of these guys is 10 to the minus 16, it's not going to create a lot of Cl2, Cl minus here, right? So let's first make the assumption that this contribution to the total chloride ion in the solution is negligible, right? And then we can do the calculation with the assumption, and then we'll check it and see, right? If this is justified. Right? So I'm going to take this reaction quotient here, Ksp, is equal to Hg2 2 plus times Cl minus squared is equal to 1.2 times 10 to the minus 16. And then what I'm going to do is I'm going to substitute in here 0.1. We're going to solve for this guy, right? So we're going to have Hg2 2 plus concentration is equal to 1.2 times 10 to the minus 16 over 0.1 squared. This is going to be 1.2 times 10 to the minus 14. I'm sorry, it's divided by, it's going to be 18, right? Let's see if I did that right. Yeah, it'll be 1.2 times 10 to the minus 18. So, right, that makes sense because this is called a common ion, and that will suppress the dissolution of Hg in this case, right? So, here's the chloride. Here's the Ksp. Here's the mercury ion. And so now we say, well, if 1.2 times 10 to the minus 18 molar dissolves, And the amount that's added here is 2 times 10 to the minus 18. Right? And this is 0.1, and we're talking about that much versus that much. Oops, sorry. This is KCl, and this is chloride from the Hg2CO2 dissolution. And it's just a tiny, tiny value that we can ignore there, you know? So, you know, we only know these constants to 2 sig figs. So if we knew this to 18 sig figs, then, oh, okay, we have to consider that, but we just don't know it that well. So they're not really that constant, you know? They're close to constant. They're not totally constant. Okay. So moving forward here, let's see. We can also have to consider, here a thing called disproportionation. And disproportionation usually involves a change in oxidation state, such that, for example, this Hg2 species here, it can react with cyanide to give one HgCN2, right? And one Hg liquid. So this is a standard state product here, but the idea here is that these two guys, they go in different directions. This is an Hg1 and an Hg1. It's 2 Hg ions, each of which is in the +1 state, right? And that reacts with a cyanide, or these two cyanides rather, and it makes 1 2+ mercury and 1 liquid mercury, right? So that's a sort of a minor thing, and I don't think I'm going to test you on it, but it's something to be aware of, right? So, so for example, in this reaction that we looked at here, right? You know, we can calculate, for example, how much Hg2 plus is in a solution of just pure water in this, right? By substituting X, the amount of Hg2 plus, Hg2 plus, right? And 2X, the amount of chloride, because it makes 2 of them there, right? And then that gets squared, right? So then, and we know this is equal to KSP. And we solve that guy for X, we get 6.7 times 10 minus 7, right? But this does not account for the other reactions, you know, where, you know, the Hg2 2 plus can react with water to make that, it can disproportionate like that, it can ion pair like that, you know, etc. Now, however, you know, these are all going to be sucking up Hg2 2 plus from the reaction. So they'll create more, they'll create some liquid mercury, they'll create some dissolved mercury forms. But if you just look at Hg2 2 plus, it will actually be equal to this value because the KSP expression is true, right? So it's just that there will be more different species of Hg in solution, right? So more of this stuff dissolves, right? More than you would predict from KSP actually dissolves because there's other reactions taking place. Okay. All right. So we'll pick up next time on foil 22. Please note that there is a homework due on Friday night, and that's for the first half of this chapter. So please get going on those guys, because I cut it down for you, but it's still a fair amount of work. Okay, guys, thanks a lot. And I will see you again on Thursday if there's no questions.
All right. See you, Professor.
Thank you. Thank you. See you
All
soon.
right,
See you
thank
soon.
you.
Thank you.
Have a good one, Dr. Terrell.
Thank
Bye.
you.
Thanks. Bye-bye, guys.